Hello YouTube, we're back. Life at the Calculus. After school has ended, this is finals week. And I thought I'd finish 107 because the last question or two in 107, which is done a lot like the other ones we did already, leads into 108, which is second order differential equation. So let's take a look at a second order differential equation, solve it by series. Let's see, where would that be? 107. It's here. Oh, it's highlighted too. There you go. This is, we did 1357, didn't we? So here's number 9. Let y equal a plus bx plus cx squared of MacLaurin series, approximating the solution curve for this differential equation. Y double prime equals negative 1. All right, and since it's a second order differential equation, we have two initial conditions. Y of 0 is 0 and y prime of 0 is 1, or maybe we could use two boundary conditions. All right, so use the given MacLaurin series to solve this differential equation. Classify this series as infinite or finite. Remember, some of these came out finite. Graph the solution and classify the function as a power function, exponential function, logarithmic, sinusoidal, logistic, or other. And solve this first order differential equation using the methods of separating of variables if possible, and whatever. Well, we're just going to do the series solution. So here we go. So this is 107, packet 107. Continued, number 9. Alrighty, so let y equal a plus bx plus cx squared plus dx cubed plus ex to the fourth plus fx to the fifth plus gx to the sixth plus. I'm doing a lot of terms just in case we might be able to get a pattern. If we could get a pattern in a general term, we can get an interval convergence. We might even be able to identify the function in closed form. Who knows? All right, so let's see. They want y double prime to equal the opposite of this. Alrighty, so what's y prime? Well, as before, b plus 2cx plus 3dx squared plus 4ex cubed plus 5fx to the fourth plus 6gx to the fifth. Forever, infinite series. Infinite MacLaurin series or Taylor series approximation near 0. And I need y double prime, really. So y double prime is, let's see, 2c plus 6dx plus 12ex squared plus 20fx cubed and plus 30gx to the fourth and so forth. All right, so let's see if we can figure out a, b, c, d, e, and f, and g. First of all, y of 0 is 0. So if I plug in 0 for all the x's in the y equals row, everything drops out but a, and y equals 0, so a equals 0. Okay. Then we say, okay, we have a second initial condition. Y prime at 0 is 1. So if we take the second line, y prime set all the x's equal to 0, everything zeroes out but b, and y prime is 1, so b is 1. All right. Now we want to set y double prime equal to negative y. Okay, so 2c is negative a, but that's 0, so c is 0. Well, the opposite of 0 is 0, okay? So c is 0. All right, fine. How about this? 6d equals the opposite of b, and b we figured out is 1, the opposite of 1 now. So I want the opposite of b, so the opposite of 1. Clean that up a little. So the opposite of b, so the opposite of 1. So d is negative 1/6. Okay. Then we get that 12e is going to be the opposite of c, because we're equating the y double prime series with the opposite of the y series, right? And c we figured out was 0, so 12e is 0, makes e 0. All right, good. How about f? 20f is equal to the opposite of the x cubed term in the y line is d. Okay, but d is negative 1/6, so 20f is positive 1/6, so f is 1 over 120. And just for fun, 30g is going to be the opposite of e, but e is 0. Whoops. 30g. So 30g is 0, makes g 0, right? All right, so let's write out the solution. I'm just going to write out the first line with A, B, C, D, and F, and G filled in. Hang on, let's bring this up a little bit. All right, so y is a, which is 0, plus bx, which is 1x, plus c x squared, but c is 0, plus d x cubed, but d is negative a sixth. Let's see. All right. Plus ex to the fourth, but e is 0. Plus fx to the fifth, and f is positive 1/20th. Plus 0 for g, x to the sixth. And does that not look familiar? It looks a lot to me like there's a pattern here. Isn't y equal to sigma, let's say n starts at 0, goes to infinity, of -1 to the n, so we're alternating signs, x to the 2n minus 1, so we have odd exponents. And isn't it 2n minus 1 the same number factorial? Right, because this is 1 over 1 factorial. This is 3 over 3 factorial. This is 5 over x to the third over 3 factorial, x to the fifth over 5 factorial. And don't we recognize that? Isn't that sine? Ta-da! So sometimes you can get a closed form answer from an infinite series, especially if you can get that pattern, and you can also test for interval convergence, which we did in class. This one has an infinite radius of convergence centered at 0. Let's see. Let me think. Is there anything else we need to say about this? Nope. And so if you go back to the beginning, y double prime equals negative y, does it make sense that y is sine? Well, the first derivative would be cosine, and the second derivative would be negative sine, so it works. And it has those initial conditions. If y is sine, y of 0 is 0, and y prime of 0, cosine of 0 is 1. Perfect. All right, one more like that. This is practice for packet 108, where we're talking about second-order differential equations that are not separable necessarily. All right, so let's do one more like this just for fun. We didn't do a lot of the evens here, but here's one. I think we did number 2 also. All right, we'll do the same kind of question. Well, actually, it's the exact same question, except, look, it says, hang on. Let me write down the problem here. Y double prime equals negative 1, right? Wait, hang on. What are you doing? Y double prime equals negative y is what we're solving. We have those two initial conditions. Well, look, we're going to do the same thing. Y double prime equals negative y again, but let's change up the initial conditions a little bit. Y of 0 is 1. Y prime of 0 is 0. Can you guess what this is? I bet you can. Let's see. Alrighty. What am I going to say here? Let's see. So number 10, let's just see this. Number 10. So same setup. Use a MacLaurin power series to approximate the solution curve for this differential equation. Use the given MacLaurin series to solve it. Classify your series as infinite or finite. Last one was infinite, right? Graph the solution and classify the function. Well, we found the general term and figured out that it was sinusoidal last time. And let's see what it is this time. I'm not going to get into Hooke's law right now. I did a lot of that stuff last year in Life After Calculus, 2013. Plus, we skipped packet 5, I think, right, which is more of the same. I'm not going to do that this year. I'm going to do 7. I'm going to do 8, which is 8 and 9, which is second-order differential equations. Then I'll go back to 6, where you have simultaneous differential equations. That's actually Calc. We're in Calc 4 now. That's actually the beginnings of Calc 5, simultaneous differential equations. And I don't know if we'll get into 10. 10 is just a bunch of loose ends, a bunch of general miscellaneous things. So I don't know if we're going to do 10. But all right, so that's the game plan. We're going to finish 7 now. We're going to base 8 on that, and then we'll go to. Well, let's look at this. Hang on. Let's look at this. What is 8? 8. 8 is using second-order differential equations to do some Hooke's law stuff. So we'll get into that. And so is 9, I think. 9 is a continuation of that. Yeah, with showing the duality between mechanics, physics, and mechanical models, and electromechanics, electromagnetism. There are a lot of parallels or dual situations is one of them. So we'll get to that. Then we'll go back to 106, and I think we'll call it quits if we have time to do all of that. All right, so let me cancel that. Let me go back here. Let me cancel that for a moment. And let's go back to here. All right, so that's what we're doing right here. All right, so y equals a plus bx plus cx squared plus dx cubed plus ex to the fourth plus fx to the fifth plus gx to the sixth. And you can add on more terms if you need them, or have less terms if we don't need them. All right, now we're trying to equate y double prime with the opposite of y, so we need y prime to get y double prime, b plus 2, cx plus 3, dx squared plus 4, ex to the third plus 5, fx to the fourth plus 6, gx to the fifth plus forever, plus, plus, plus. All right, and then y double prime is 2cx plus 6dx squared plus 12e, sorry, I skipped power, that's x, and then it's 12ex squared plus 20fx cubed and 30gx to the fourth, right? Okay, so again, we're equating y double prime with the opposite of y, but the initial condition y of 0 equals 1 gives a is 1, and the initial condition y prime of 0 gives 0 makes b 0. So last time a was 0, b was 1. And so 2c is the opposite of a, so 2c is the opposite of 1, so c is negative 1/2. Okay, good. 6d is the opposite of b, and that means, well, b is 0, so d is 0. Okay. 12e is the opposite of c, but c is a half, so the opposite, negative half, so the opposite of negative 1/2 is 1/2. So e is 1/24. Alrighty. 20f is the opposite of d, and d is 0, so 20f is 0 makes f 0. And last but not least, 30g is the opposite of e, but e is 1/24. Oops, it's a 30. So the opposite of 1/24, and so g is going to be negative 1 over 720. All right, so let's write this out. Let's see here. So a is 1. Let's write this out. Y equals a, which is 1, plus bx, which is 0x, plus cx squared, which is negative 1/2, so negative 1/2 x squared, plus dx cubed, but d is 0, plus ex to the fourth, so it's plus x to the fourth over 1/24, because e is 1/24th, and fx to the fifth, but f is 0, and plus gx to the sixth, but g is negative, so negative 1x to the sixth over 720, plus, plus, plus. And do you recognize this pattern? Well, let's see. Y is sigma. Let's do alternating signs. Let's do even powers. And is it those same powers factorial? X to the 2 over 2 factorial, x to the 4 over 4 factorial, times 3 times 4, yeah. X to the 6 over 6 factorial, times 5 times 5 times 6, yeah, that's right, that's right. And so that starts with n equals 0. Goes to infinity, and isn't that cosine? Yay. Isn't it true that the derivative of the second derivative of cosine is the opposite of the cosine? Y double prime equals negative y. Let's see, the derivative of the cosine is negative sine, that's y prime. The derivative of negative sine is negative cosine, that's y double prime. So y double prime does equal y, or the opposite of y. And the initial conditions isn't the cosine of 0, 1, and the derivative of the cosine or sine of 0, 0. Yes, so this is perfect. Okay, and we're going to use that result in packet 108. So let's say 107, it is done. All right, so that was a quick finish to 107. We'll use that result in 108 and 109. We'll go back to 106. And I think that will do for this year. We covered stuff in 110 and 105 in the previous year, so it's not like I'm skipping it. You can find those on my YouTube channel, like DiffEqus 2012, like DiffEqus 2013. so forth. Alrighty, so